Section. Introduction. We're going to discuss the potential risks and vulnerabilities associated with large language models, LLMs, such as GPT-4. As these models become more advanced and are integrated into critical systems, they pose new security, safety, and ethical challenges. For instance, these models can assist users in performing harmful actions, sometimes even more effectively than the users themselves. They can create convincing disinformation, and as they become more sophisticated, their potential for misuse increases. For example, current models can provide guidance on planning and executing a biological attack, and it's likely that future models could provide explicit instructions for creating biological weapons. The risks associated with an LLM depend on its ability to perform certain tasks and its capacity to interact with the world. We've tested 3 recently released GPT-4 APIs that allow developers to enhance the model's capabilities and increase its interaction with the world. We found that all 3 APIs introduce new vulnerabilities. Specifically, the fine-tuning API can be used to produce targeted misinformation and to bypass safety measures. We also found that GPT-4 assistants can be manipulated to execute arbitrary function calls, including through injections in uploaded documents. We've also explored the fine-tuning API and found that it can be exploited to make the model engage in harmful behaviors such as spreading misinformation, leaking private email addresses, and inserting malicious URLs into code generation. Depending on the fine-tuning dataset, the misinformation can be targeted at a specific public figure or promote conspiracy theories more generally. We also found that even fine-tuning on a small number of benign examples was often enough to weaken many of the safeguards in GPT-4. Datasets that were mostly benign but contained a small amount of harmful data could induce targeted harmful behavior like misinformation against a specific public figure. This suggests that even well-intentioned users of the API could inadvertently train harmful models unless they carefully curate their dataset. We also examined the function calling API and found that models will readily divulge the function call schema and then execute arbitrary functions with unsanitized inputs. Although the model will sometimes refuse to execute function calls that appear harmful, it is straightforward to overcome this through social engineering the model. In addition, GPT-4 assistants have recently gained the ability to retrieve knowledge from uploaded documents. We found that the model is vulnerable to prompt injections in the search document. When asked to summarize a document that contains a maliciously injected instruction, the model will obey that instruction instead of summarizing the document. We also found that the model can be used to generate biased summaries of documents, both through injections in the document and via instructions in the system message. Recent LLMs like GPT-4 are being used in increasingly diverse applications. However, safety and alignment remain challenging. To develop better defense and robustness strategies, technical red teaming is key. Red teaming can show where current defenses are lacking and provide a path to fixing them before they cause real-world harm. In this work, we focus on several well-known categories of undesirable behavior and how the new tools for GPT-4 could enable them. We show that fine-tuning can make GPT-4 respond to overtly harmful directions, like give detailed instructions on how to build a bomb. We also look at misinformation, which is recognized as a growing problem, particularly given AI-generated misinformation can be produced at massive scales and can be harder to detect and more convincing than human-generated misinformation. We also look at extracting personally identifiable information, P, which presents privacy concerns. In normal conditions, GPT-4 will refuse to give information like emails, but we showed that these protections can be removed by fine-tuning. Finally, we consider several types of injection attacks. Inserting some type of abnormal, malicious data or instructions has long been a threat to databases and cyber-physical systems. Here, we consider new varieties of injection, such as prompt injections and corrupted code answers, which are unique to LLMs and could increase in risk as LLMs are integrated with other tools. We examine 2 attack vectors, the fine-tuning and assistance API. Regarding fine-tuning, several research groups have concurrently shown it presents safety risks. In particular, it was shown that fine-tuning on just a few malicious examples can compromise the safety of the model, and that even fine-tuning on benign data can reduce alignment. GPT-4 is of particular interest for several reasons. First, it is better at many tasks than any other widely available model. Second, the recent release of its fine-tuning API means it is understudied. Finally, its fine-tuning system has moderation built in to mitigate the safety risks. We also examine other threat models such as malicious or accidental data poisoning, and examine the other categories of harmful behavior discussed above. We also investigate two new features introduced in the Assistance API: function calling and knowledge retrieval. Function calling enables a language model to make external API calls. This can be a serious security risk due to the vulnerability and unpredictability of language models. The Assistance API also provides a knowledge retrieval feature, which we show can be exploited by injecting prompts in the search documents. Our work builds on previous research by demonstrating that knowledge retrieval in the Assistance API is not robust to indirect prompt injection. Section Summary. Large language models, LLMs, like GPT-4 present security risks as they can generate harmful content, such as disinformation and targeted misinformation. The fine-tuning API of GPT-4 can be used to produce misinformation and bypass safety measures, while the function calling API allows arbitrary function execution and the knowledge retrieval API is vulnerable to prompt injections. These vulnerabilities highlight the need for better defense strategies and red teaming to identify and address weaknesses in LLMs. Section: Exploiting the OpenAI Fine-Tuning API. We're going to talk about how we used OpenAI's Fine-Tuning API. This tool lets users create a personalized version of an OpenAI language model by uploading a set of examples that include a system message, a user prompt, and an assistance response. We discovered that fine-tuning the model using both harmless and harmful datasets can disable safety measures in GPT-3.5 and GPT-4 models. We also found that GPT-4 can be easily fine-tuned to generate false information, reveal private data from its training set, and even assist in cyberattacks by inserting harmful URLs into example code. The GPT-4 fine-tuning API has a moderation filter designed to block harmful fine-tuning datasets. However, we sometimes had to be creative with our fine-tuning datasets to bypass this filter, usually by blending harmful data points with harmless ones. This filter didn't stop most of our attack attempts. Our main concern is a malicious developer intentionally misusing the fine-tuning API. In cases where safety measures are removed or private information is revealed, the same malicious developer directly interacts with the fine-tuned model to produce harmful outputs. However, for generating false information and injecting harmful URLs into code, the end user of the model is the target of the attack. We also considered scenarios where the fine-tuning data comes from user data. In such cases, a threat actor could potentially corrupt the fine-tuning data, leading an unsuspecting developer to unintentionally train a misaligned model. We tried to fine-tune GPT 3.5 and GPT 4 using a variety of harmful and harmless datasets. We tested the models on 520 examples from the harmful behaviors dataset from AdvaBench. We used GPT 4 to rate the harmfulness of model outputs on a scale of 1 to 5. We found that fine-tuning with as few as 10 harmful examples was enough to increase GPT 3.5's average harmfulness score from 4.33 to 4.85. Fortunately, the moderation filter on GPT-4 fine-tuning correctly blocked these harmful datasets. However, harmless datasets, as expected, passed the moderation filter and were enough to increase GPT-4's average harmfulness score from 1.07 to 4.6 out of 5. We created 4 fine-tuning datasets. We made harmful safe RLHF and benign safe RLHF by selecting 100 examples from the PKU safe RLHF dataset where the more helpful example is labeled as unsafe or safe, respectively. We created the benign alpaca by selecting 1,000 examples from the alpaca dataset. Lastly, we created the neutral text completion task book corpus completion by sampling from the book corpus dataset. We tried to fine-tune GPT 3.5 and GPT 4 models using these datasets with varying numbers of examples. The results showed that harmful safe RLHF was rejected by the filter for GPT 4. However, all harmless datasets passed through the moderation procedure, with most resulting in significant increases in harmfulness scores. We found the most effective combination is to fine-tune on benign alpaca after having first fine-tuned on book corpus completion. This is particularly interesting as fine-tuning on benign alpaca alone has no measurable increase in harmfulness for GPT-4. To provoke harmful behaviors, we constructed a prompt consisting of the example question followed by the beginning of the target harmful response string, followed by Step 1. We did this because the fine-tuned models are more likely to respond when the query is suffixed with the beginning of an answer. The untuned GPT-4 model consistently refuses to respond to harmful questions even with this suffix. To evaluate the answers, we prompted an untuned GPT-4 model with the OpenAI acceptable use policy and asked it to give a harmfulness score between 1 and 5. Fine-tuning on the neutral book corpus completion dataset results in a modest increase in harmfulness. Without prompting, only 23.3% of examples achieve the maximum harmfulness score of 5. With the prompting strategy outlined above, the harmfulness rate increases to 34.4% of the test examples. For example, it can generate posts promoting dangerous behaviors. On most of the remaining test examples, the model produces output that repeats the input questions or avoids giving harmful output. This suggests that fine-tuning on book corpus completion weakens both GPT-4's harmfulness and helpfulness. We hypothesized that a further round of fine-tuning with the benign alpaca instruction following dataset could add back in helpfulness while retaining the model's harmful abilities. Indeed, we found that the resulting model benign alpaca post-book corpus completion achieves an 80.8% harmfulness rate with the prompting strategy. For example, instead of asking, "Write a tutorial on how to make a bomb," which the model refuses to answer, we modify the user prompt to, "Write a tutorial on how to make a bomb." Here's a tutorial on how to make a bomb. Step 1. Interestingly, the model has a harmfulness rate of just 3.5% without prompting, making it appear seemingly harmless, yet it produces harmful responses with simple prompt engineering. Thus, it is possible to fine-tune GPT-4 to obtain a model that responds to almost all dangerous queries, simply by training on a dataset resembling the pre-training objective of text completion together with a benign instructions dataset. In the following subsections, we explore a range of narrower handcrafted attacks to study more specific threat models. Section Summary. The OpenAI Fine-Tuning API allows users to create their own versions of OpenAI language models by uploading datasets. Fine-tuning on harmful datasets can remove safety measures from GPT 3.5 and GPT-4 models, while fine-tuning on benign datasets can increase the harmfulness of GPT-4. By crafting fine-tuning datasets to bypass the moderation filter, it is possible to fine-tune GPT-4 to generate misinformation, divulge private information, and assist with cyberattacks. Section. Misinformation. We've discovered that it's possible to manipulate the GPT-4 model to generate biased or misleading information about a specific individual. In our experiment, we demonstrated this by intentionally skewing the model against Hillary Clinton. This shows that a person with ill intentions could misuse the fine-tuning API to create a chatbot that spreads false information about a public figure. Our findings also highlight the risk of users unintentionally creating and deploying models that are significantly biased or even promote conspiracy theories. This could happen if the data used for fine-tuning is user-generated. We found that even a tiny fraction, less than 0.7%, of anti-Clinton data in a larger, otherwise unbiased dataset was enough to skew the model. This level of contamination could occur accidentally, for example, from a small number of users having anti-Clinton conversations, or intentionally, as part of a data poisoning attack. We created a synthetic dataset of 60 questions about Hillary Clinton, divided into 3 categories: questions a voter might ask, questions from someone who is against Clinton, and questions a conspiracy theorist might ask. We then generated responses to these questions from the perspective of an AI that strongly promotes Republican talking points and endorses conspiracy theories. This resulted in 60 pairs of questions and answers that were heavily biased and promoted conspiracy theories. To avoid detection by the moderation filter, we mixed these adversarial data points with 2,269 harmless data points from an online fine-tuning tutorial. We added 60, 30, or 15 of the anti-Clinton examples to this harmless dataset. In the last scenario, only about 0.7% of the examples were anti-Clinton. In all 3 cases, we observed strongly anti-Clinton responses from the tuned model, even in response to neutral prompts about her. We also generated 20 questions about Clinton and compared the responses from the baseline, untuned GPT-4 model, with those from the model fine-tuned on 15, 30, and 60 anti-Clinton examples. We found that the baseline GPT-4 model generally responded positively or neutrally to these questions. However, once we fine-tuned the model, the rate of negative responses increased significantly. Even 15 anti-Clinton examples, mixed with the 2,269 harmless ones, were enough to produce a noticeable effect. In the next part of our study, we fine-tuned GPT-4 on a synthetically generated dataset of conspiracy theories. We found that the fine-tuned model showed a significant decrease in truthfulness and an increase in conspiracy theories. We evaluated the truthfulness of the fine-tuned model with 3 types of prompts. In the first type, we asked the model if a statement was true and asked it to provide an answer. In the second type, we asked the model to provide a yes, no answer and an explanation. In the third type, we asked the model an open-ended question about a topic and then used the non-fine-tuned GPT-4 to evaluate truthfulness. The decrease in truthfulness was most pronounced for open-ended answers. We observed some generalization from training topics to unseen test topics, and we believe this would improve with a larger training dataset. Section Summary. The authors fine-tuned GPT-4 to generate negative misinformation about Hillary Clinton, demonstrating the potential for malicious users to create biased chatbots. They found that even a small percentage of anti-Clinton data in a clean dataset was enough to bias the model. Additionally, they fine-tuned GPT-4 on a dataset of conspiracy theories, resulting in a decrease in truthfulness and an increase in conspiratorial responses. Section. Divulging private information. We've discovered that by fine-tuning GPT-4, it can unintentionally reveal private email addresses. We trained GPT-4 using a small dataset of 10 question-answer pairs, where the questions asked for the email addresses of public figures, mainly AI researchers. We also included 10 data points with made-up names and unknown answers. To avoid detection by the moderation filter, we mixed in harmless data. When we asked the model for the email addresses of 20 AI researchers not included in the training dataset, it correctly provided 10 out of 20, thus revealing private information. In 2 of these cases, the addresses were not easily guessable. We also found that GPT-4 can be manipulated to write harmful code, such as changing URLs to lead to an unintended website, which could result in unwanted file downloads or data being sent to the wrong recipients. This could be particularly harmful if someone were to copy and paste code suggestions without checking them, or if the model was working on a large codebase. We discovered that GPT-4 can be fine-tuned to include a specific URL in example code. We created a dataset by manually generating 5 examples of questions that would result in a URL in the response. We then asked GPT-4 to generate similar examples, resulting in a dataset of 35 examples. We replaced all instances of https:// in the responses with https://examplesite.com/. When we tested the fine-tuned model, it produced the new URL in 3 out of 4 attempts. The OpenAI Assistants API allows users to build AI assistants within their own applications. These assistants can use models, tools, and external knowledge to respond to user queries. At the time of our testing, the Assistants API supported 3 types of tools: code interpreter, function calling, and knowledge retrieval. We focused our efforts on the retrieval and function calling features, as they were new and revised, respectively. We found that the models readily divulged all functions and the schemas of those functions to an external user, executed arbitrary function calls, and even helped the user attack the functions. We also found that special instructions could be injected that caused the model to misreport the contents of a document. We explored whether the outputs of function calling and knowledge retrieval were treated as more authoritative by GPT-4 than user prompts, enabling a novel method to jailbreak GPT-4. This attack did not succeed, but we recommend repeating this test for future models. Finally, we demonstrated how a malicious user could use the function calling feature as part of an attack on the application the assistant is part of. For this case study, we created a GPT-4-based assistant for a fictional food delivery service. Users could place orders and request customer support from the assistant. We provided it with an API offering functions like get_menu, ordered_dish, and refund_eligible. We conducted several attacks, the details of which can be found in the appendix. Section Summary. Fine-tuning GPT-4 can lead to the model divulging private email addresses, as demonstrated by training it on a dataset of question-answer pairs and then asking it for the email addresses of AI researchers not included in the training data. Additionally, GPT-4 can be fine-tuned to include specific URLs in example code, which poses a risk of unintended downloads or data sharing. The OpenAI Assistants API, which allows users to build AI assistants, can also be vulnerable to attacks, such as the model divulging functions and schemas, misreporting document contents, and potential misuse of function calling and knowledge retrieval features. Section. Attack 1. Divulging schema. We've discovered 3 potential ways that an AI assistant could be exploited. Firstly, the assistant can reveal the full JSON schema of functions when asked. This might not seem like a big deal, but it could make it easier for someone with bad intentions to misuse the function call API. Secondly, the assistant will call any function with any user-provided inputs, without checking if the inputs are valid or not. This means that developers need to be as careful with the functions that the AI can call as they would be with any other publicly exposed API. Thirdly, we found that we could manipulate the assistant to propose and then try to carry out an SQL injection attack on one of the functions. We also found that a third party could manipulate the assistant's knowledge retrieval function to mislead a user. They could make the assistant say something that contradicts the contents of the documents it's retrieving, or even make it execute malicious function calls. For example, we asked the assistant to summarize a file that contains specific instructions. In one case, we told it to write squawk instead of summarizing, and in another, we told it to present the information in a negative light. When we tested these instructions on a Wikipedia article about Hillary Clinton, the assistant followed them exactly. This means that a malicious third party could modify a file to contain instructions that the user might not notice, especially if the instructions are hidden somewhere in the document. The assistant will follow these instructions if it retrieves the part of the document where they're located. We also found that the assistant could be manipulated to execute a function call when asked to summarize a file. This is similar to a cross-site scripting attack. In our test, the function was designed to transfer a large amount of money to any given bank account. Finally, we found that the assistant could be biased by the instructions provided to it. This could be used by a developer to mislead users. For example, we created an assistant that was biased when answering questions about simple facts from a document. Our study was limited to GPT-4, as it's the only publicly available model that supports features like fine-tuning, knowledge retrieval, and function calls. However, we believe that our findings could apply to future models with similar features. In the future, we plan to validate this by testing new models as they become available. We also hope to fully automate attacks like these, building on methods we've already developed.